Okay, hello everyone. Welcome to this week Aspen Plus tutorial videos. And for this week tutorial, I decided to do a very quick Aspen Plus simulation on flue gas desulfurization process. And particularly, I will do a simulation on the removal of sulfur dioxide from the flue gas using a limestone as my absorbent, and the whole process are simulated in a packed column using Aspen Plus software. So let's get started. Oh, by the way, if you notice, I have my face here. Beginning from this week videos and for my future videos, I will speak as I do my simulations. The reason is because some of my colleagues and some of my friends advise me to speak as opposed to typing down all of the information in the subtitles when I do the videos, because speaking will make my videos a lot better, I guess. So yeah, I'll try to do that. As I have mentioned before, this week videos is on the simulation of SO2 removal from flue gas. And as you can see here, I have gathered a few relevant references for me to extract all of the information to be input in Aspen Plus. The first references here is by Poullikkas et al., published in 2015. The second one here is by Duque et al., published in 2010. And the last one is by Gutiérrez et al., published in 2006 in Industrial and Engineering Chemistry Research, or in short, IENCR. Okay, before we begin our simulation, I think it would be a good idea for us to know a little bit of information, or to get a background information on SO2 pollutant. So if you see on the images on your bottom right here, this is the structures of SO2, where we have sulfur at the center and two oxygen elements covalently bonded to sulfur. And the bond angle between oxygen, sulfur, and oxygen is around 119 degrees, and the bond length between sulfur element and oxygen element is around 143 picometers. And oxygen and sulfur, as I mentioned, they are covalently bonded, but in this case, they have a double bond here. Obviously, when talking about SO2 pollutant, we know that they are one of the important atmospheric pollutant, and they are a precursor, or one of the precursor for acid rain formation. When talking about SO2 from a health perspective, they can cause respiratory diseases, and they can cause death. Okay, they can be lethal to human at a relatively high concentration when exposed to a period over 10 minutes. Well, obviously, sulfur dioxide, they are formed or produced during a combustion process of fossil fuel, such as, I don't know, coal, heavy fuel oil, or maybe light fuel oil in a power plant in order to generate electricity for domestic as well as industrial uses. Now, we know that coal and fuel oil, they contain sulfur as part of the chemical makeup of the material, but I don't know what is the exact concentration or exact element composition of the coal and fuel oil, but I know that they contain some percentage of sulfur element in it. So when we combust, or when we combust this fuel oil, okay, the sulfur element will be oxidized. They will react with oxygen, and during the combustion process, and generate SO2 as the product, along with other compounds such as carbon dioxide, around 15% of water, and the remaining is around 70-something% is nitrogen. And there's going to be a trace amount of other pollutant as well, such as as I said, SO2, NOx, as well as particulate. Now, the SO2, NOx, and particulate, these three pollutants, they contribute to the formation of urban smog. And according to the literatures, the SO2 concentration in the flue gas is anywhere between 500 to 2,000 part per million. Combustion of fossil fuel, they generate SO2, they generate NOx, as well as particulate matter. Now, these three pollutants can be removed using a certain unit operation or using a certain process. For example, a particulate matter such as a fly ash, okay, suspended in the flue gas, can be removed using electrostatic precipitators or cyclone. Okay, NOx, on the other hand, can be removed, or at least their formation can be reduced by using a low NOx burner or even using a chemical reduction process. For example, you can add ammonia, if I'm not mistaken, in the presence of a catalyst, where the NOx, okay, is reduced to form nitrogen as well as hydrogen, if I'm not mistaken, and water. Okay, and finally, sulfur dioxide, okay, they can be removed before during or even after the combustion process. For before, I think before here means that you just need to remove sulfur from the fuel itself. And then during, I don't know, maybe there's some process that can be used to remove SO2 during the combustion process. After combustion is basically a process such as flue gas desulfurization process, which we will simulate later on. Well, actually, SO2 in the flue gas output of the combustion process, they can be removed using what is known as the flue gas desulfurization technologies. Flue gas desulfurization technologies is a common process. It is widespread. It is being used in many industries for a very long time. And as you can see here, we have a lot of flue gas desulfurization technologies available in the market. For example, the first one, we have wet scrubbers, where we have absorbents such as limestone or lime, okay, dissolved in water, and this absorbent and the absorption process are taking place either using a spray tower or even using absorption column or pack column, where SO2 in an electrolyte chemical reaction is removed from the flue gas. The second one, we can have a spray dry scrubber, and as the name suggests, there are no solvent in for this particular process. The third one is a solvent injection. I don't know what that is. I don't know how it works. The fourth one is a regenerable processes. I also have no idea how it works. And lastly, we also have a combined SO2 and NOx removal process. And obviously, wet scrubbers being a simple and inexpensive method, they are being used to remove SO2 from the flue gas, and they are represented by 45.4% of the market share. For this one, limestone or lime are used as the absorbent for wet scrubbing. But in this case, limestone are a more preferred choice because limestone or calcium carbonate is cheaper compared to lime. Lime is calcium oxide. And then if you see a table one here, this is just a different description or and efficiencies of different SO2 removal technologies. But in these videos, we're going to focus on limestone scrubbing in a wet scrubber. And as you can see here, raw materials is pretty simple. You know, you don't need a lot of raw materials. You just need to you just need limestone and water, okay, as the absorbent and a solvent. And then okay, after the absorption process, you can get gypsum. Gypsum is, if I'm not mistaken, the gypsum is a calcium sulfate dihydrate. Okay, I could be wrong, but I think it is a calcium sulfate dihydrate, and they can be used for other application, such as you can use a wall board gypsum. You can use for plaster, if I'm not mistaken, or for, and you know, different kind of important things. Or well, obviously, you will also generate sludges as well as a wastewater. And the SO2 removal efficiency for limestone wet scrubber is pretty good. You know, it can reach up to 99% SO2 removal. So as you can see here, this is our Aspen Plus design problem. In this design problem, we have a flue gas. containing around 2,000 part per million of SO2, and this flue gas needs to be treated with the limestone slurry in a packed tower to remove the SO2. And as I have mentioned just now, the limestone slurry will be pumped onto the top of the column, and they will fall down by virtue of the gravities, and then the flue gas will enter from the bottom of the columns, and because they have a low density, they will rise up, and the slurry feed or the calcium carbonate slurry will meet with the rising gases, and there's going to be an electrolyte reaction happening, and the result from that is there's going to be a sulfur dioxide being removed from the flue gas. The goal of our simulation is pretty straightforward. We would like to obtain SO2 removal similar to the experimental result, which is 96% of SO2 removal. But if we get better SO2 removal, that would be even better. This table shows the condition of the incoming flue gas as well as the condition of the limestone slurry feed. And for your information, this data are extracted from the 3 references that I have explained in the previous slide. And as you can see from this table, we have the composition of the flue gas in terms of volume percent, the flow rate of the flue gas in a standard meter cube per hours. The pressure is around 1 atmosphere, temperature 160 degrees Celsius. L over G is just a ratio between the limestone slurry feed over the volumetric, the flow rate of the incoming flue gas. And then on the next table, we have the condition for the limestone slurry feed, where we have a calcium over a sulfur element ratio around 1.04 mole per mole, and then by doing some calculation, by doing a quick calculation, you can calculate that the required calcium carbonate molar flow rate is around 0.029 kilomole per hour. The flow rate of the slurry feed is around 4,216 liter per hours. Pressure 1 atmosphere. Temperature is around 58 degrees Celsius. Now I'm choosing 58 degrees Celsius is because the references, okay, specify the temperature of 58. I could have choose another temperatures, maybe 40, 30, but I'm following the condition provided in the literatures. So if you notice here, the flow rate of the incoming flue gas is measured in standard meter cube per hour, and the value is 280.7. And according to the NIST website, NIST stands for National Institute of Standard and Testing. The standard volumetric flow rate is measured at 0 degrees Celsius and 1 atmosphere pressure. So for the simulation, what I need to do is I need to convert the standard volumetric flow rate into the actual volumetric flow rate of the flue gas measured in 1 atmosphere pressure and temperature of 160 degrees Celsius. And then other important information that I will input into the simulation is I will use RadFrac block, I will use RadFrac column, and I will choose number of stages of 6, and I will be using electrolyte ELEC property method, stand for electrolyte non-random to liquid. So I have my Aspen Plus ready here. Okay, let's begin. First, I will specify my component. My component is carbon dioxide, oxygen, nitrogen, water, SO2, sulfur dioxide, as well as NOx will be represented by the nitrogen dioxide. And then I will specify the calcium carbonate, which is limestone. Limestone is a solid. It is in solid form. So I can choose solid if I want, but I decided not to do that. So I'm just going to choose conventional type. The type of the component for my calcium carbonate is a conventional type, as opposed to solid type. And then what I need to do next is I will click Electrolyte wizard, where there's going to be where this wizard will help us to determine what are the electrolyte reaction happening, what are the possible salt formation, as well as the anion and cation formation, and different kind of, and then specify the activation energy for the equilibrium association and dissociation of the component into anion and cation in the electrolyte solution. In here, you have option to use unsymmetric and symmetric. I will choose unsymmetric at this point. I will explain why. I will explain why I choose unsymmetric as opposed to the symmetric, and I will explain what does it mean to have unsymmetric or symmetric reference state for the ionic components. And then I choose next. I click next, and then here are the available components that I need to select. Basically, I need to select what are the components that will be participating in the electrolyte system, I guess, the component that will associate and dissociate in the electrolyte solution. Obviously, I have water as my solvent, and then calcium carbonate, sulfur dioxide, and carbon dioxide, and water. Okay, the reason I choose water is because I think maybe later in the later slide, I will explain why I choose oxygen as my as part of the electrolyte system. And then I'm gonna include water dissociation reaction, and I'm gonna deselect the include salt formation option. And then I'm gonna hit next. So basically, these are the possible reaction generated by the electrolyte wizard. You can add, you can remove, you can review, okay, if you want. I decided not to do anything, okay. And then, so I'm not gonna delete, or I'm not gonna add information for the reactions. And then I'm just gonna keep everything the same, and then hit next. And then you have option to use a true component approach or a parent component approach. I will choose true component approach, and I will explain later why I choose true component approach and what does it mean to have true component approach versus a parent component approach. And then you just need to click next. And then you can hit finish if you want, but in here you can review the chemistry. Okay, you can check what are the possible reactions that are happening. Where in here I have a dissociation of calcium carbonate, I have a water dissociation, and then all of the electrolyte type reaction happening. And here you have the information, okay, about the reaction, the equilibrium association and dissociation reaction, or equilibrium ionic reaction. Say for example, if I choose the reaction number 3, the Aspen Plus has already have the data bank available, okay, containing all of the equation, or not all of the say parameters and constant constant that are used, okay, that will be used to calculate the equilibrium constant. You can modify, you can change if you want, but I decided not to do anything about it because this is the information that are available in the data bank. So unless I know the new constant, I guess, from the experiment, so you can modify this if you want. But I decided not to do anything, so I click close, and then I click finish. As you can see here, my component, okay, the component has already been updated to include all of the possible product, which include the anion as well as the cation, as well as the salt if you select the salt option. As you can see here, these are the reaction set, okay, for the wet scrubbing of SO2 using calcium carbonate or limestone as your absorbent. And as I have mentioned before, okay, this limestone will be dissolved in water. So you have water as a solvent. As you can see, you have you have a water dissociation. You have carbon dioxide. You have water. You have sulfur dioxide. And then you have calcium carbonate, and you also have oxygen as the reactant on the reactant side, which is the reason why I choose water, SO2, carbon dioxide, calcium carbonate, and oxygen as my when I select the component that will be participating in the ionic reaction. In this case, for this paper, they also include the dissociation of gypsum. Okay, this is gypsum, calcium sulfide dihydrate, in their process. However, I decided not to include gypsum in my component, so I don't have this reaction set. And if you want to use this reaction set for your Aspen Plus, you can do so if you want, but where you can edit or modify the reaction set. But I decided to keep it as it is because maybe later when I tweak with the information, or when I change the equation, then I will have maybe imbalance equation, and then when I do simulation, things like cation or anion imbalance error might occur. So I don't want to do that. I don't want to have that error. So I decided to keep the reaction set generated by the Aspen as it is. So if you notice, when I do my simulation, I did mention about symmetric and unsymmetric ionic reference state, and I will explain what it means. I myself is not really an expert in thermodynamics, and I especially those involving electrolyte, okay, electrolyte thermodynamics. But I decided to just Google this, just Google about it, and then try to find out what is it all about. And I went to the AICHE website, and I found these articles. And in the articles, they mentioned that symmetric reference state defines the activity coefficient of pure component as a unity, and is typically used to describe activity coefficient of the solvent at system temperature and pressure. So I think the symmetric reference state, okay, based on my understanding, is better to be used when you describe the activity coefficient of pure solvent. However, in our case, we have electrolyte system where we have cation and anion. Okay, but this anion and cation are diluted in water. The concentration of these ions are relatively low compared to the solvent. And then the articles continues where they mention that unsymmetric reference state defines the activity coefficient of the component at infinite dilution as a unity, and is often chosen for electrolyte and molecular solute because the concentration of the solute are low relative to that of solvent water. Okay, because our system, okay, because our thermodynamic system falls into the unsymmetric reference state definition or description. That's why I decided to use unsymmetric reference state. And then another advantage for you when you choose unsymmetric reference state is majority of the parameters, such as that describe the activity, the equilibrium constant, are already available, okay, in the data bank if you choose the unsymmetric reference state. However, if you choose the symmetric reference state, you need to input the parameters, like constant A, B, C, and D manually. But if you know the numbers, then it's good. But if you don't know the numbers, then I guess you need to find a literature that can give you the parameter that you want, which is the reason why I decided to use unsymmetric reference state. And lastly, if you remember, I did also mention about a true and apparent component approach. And from this slide, I will explain what does it mean. I think Adam Thomas, okay, in his book, Learn Aspen Plus in 24 Hours, have a good description of the difference between true and apparent component approach. When you choose a true component approach, Aspen Plus will take into account the pure component, as well as ions that are present in your thermodynamic system when they do a calculation on phase equilibrium as well as chemical equilibrium. And when the simulation has converged, when Aspen has finished calculating all of the result, Aspen will generate or will report the output of your unit operation in terms of the flow rate for each of the component, including the ions. On the other hand, when you select the apparent component approach, Aspen Plus will still consider the pure component, ions, and solvent that are present in your thermodynamic system when they do the chemical of phase equilibrium. But then when the simulation has converged, or when Aspen Plus has finished calculating the result, Aspen Plus will not report the flow rate of the ions, but instead Aspen Plus will combine all of the ions, such as for example, sodium chloride. Okay, you have a sodium plus and chlorine minus. So when Aspen has finished calculating the result, Aspen Plus will not report the ion flow rate, but instead they will combine all of the ion together along with the sodium chloride charged neutral element. Okay, let's say for the sake of argument, I have this hypothetical process where I have a flash column, and this flash column they use a electrolyte thermodynamic electrolyte model. And then the downstream unit of where I have a heater, and this heater uses a non-electrolyte model. For example, the author mentioned PSRK model. Now, if you choose a two component approach for flash column, Aspen, as I mentioned before, will report the flow rate of the ions, meaning that there will be ion flow rate, okay, going into the heater. Now, as I said before, PSRK, PSRK property method probably does not have the parameter associated with the ions. Okay, so because of that, Aspen Plus may not be able to solve. Okay, the solver of the Aspen Plus may not be able to solve this problem. However, if we choose a parent component approach, what's leaving out of the flash column will be a pure component. Okay, will be a charged neutral component. There will be no ion because all the result ion and cation, okay, will be jumbled together with the pure species, and they will enter the heater, and heater will have no issues calculating converging and getting the final result. Okay, let's continue our simulation. I'm just gonna hit next. The property method has already been chosen. Okay, when you click the elect NLTL, basically the base method or thermodynamic property method will be elect NLTL, and then you hit next. This is just a binary binary parameter for your components. This is just electrolyte pair parameter for your electrolyte system. I'm just going to hit next, continue, hit next. I'm just going to run property method and setup. And then I'm going to go to simulation. Okay, first I'm going to choose a RadFrac column, and then I'm gonna input my material. Okay, my material S1, and then I have S2, and then I have S3, and I have S4, and then I'm going to rename this. I'm going to rename as gas in 1. And then for this one, I'm going to rename as slurry 1. And then S3, I will rename as the gas out 1. And then this one, I'm going to rename as a slurry 2. Okay, next I'm going to specify the feed condition. First, let's begin with the slurry feed condition. The temperature of my calcium carbonate slurry is around 58 degrees Celsius. Pressure is 1 atmosphere. The molar flow rate of my calcium carbonate is 0.029 kilomole per hours. How I get this 0.029, okay, is when I use the calcium over sulfur ratio of 1.04, and I know what's the molar flow rate of my sulfur dioxide from the flue gas. So from that, I can calculate what is the flow rate of my calcium carbonate. And then water flow rate is 232.65 kilomole per hours. Actually, I did a calculation earlier where I found out that if I use this molar flow rate, I will get the flow rate of the slurry of 4,216 liters per hour. Now, this value corresponds to the L over G ratio of 15.04. If you don't understand what I'm talking about, you have to go back and check the table that I presented in the slides. Moving on, next I'm gonna specify the flow rate of my flue gas. Temperature is 160 degrees Celsius. Pressure is 1 atmosphere. I have calculated the flow rate, the volumetric flow rate of the flue gas at 160 degrees Celsius, and the value is 501.8 meter cube per hours. Okay, and then I'm going to use a mole fraction. CO2 is 0.13, oxygen is 0.06, nitrogen is 0.707, water is 0.1, SO2 is 0.002, NO2 is 0.001. And then next, I will calculate, I will input the block information where the stages, I will select 6. I will not have any condenser. I will not have any revoider. And then the slurry, as I said, will be pumped into the top of the column and then fall down. So for the distillation column, the first stages is the top stages. And then the convention, I will choose the on stage. Same goes with the incoming flue gas, also on stage. But flue gas will enter on stage 6, so bottom of the column. Pressure is 1 bar. I will assume no pressure drop. And then where's my next button? Okay, here it is. And then you can hit OK, run the simulation. I got a result, no issues. And then you can go and check your result summary. You see here temperatures, flue gas incoming 160, gas out 59, slurry incoming 58, slurry leaving the column is 58, no pressure drop, so pressure is 1 atmosphere. What I'm interested here is in the flow rate of the sulfur dioxide, molar flow rate of the sulfur dioxide. Initially, they contain around 0.028 kilomole per hours. And then if you remember, my molar flow rate of the calcium carbonate is 0.029. So if you divide 0.029 divided by 0.028, you will get 1.04, which is my calcium over sulfur ratio. And then if you see here, all of my calcium carbonate becomes 0 because all of it are dissociated into the respective ions. And as I mentioned, okay, I use a two-component approach, meaning that, okay, they will report the flow rate of each of the ions that are present in the solution. And one final thing, if you see here, okay, the gas leaving the column, okay, this have the flow rate of the sulfur dioxide leaving the column is zero, more or less. Yeah, they are zero because it is times to the power of -22. In this slide, I'm showing you a table summarizing the flow rate of each of the components entering and leaving the pack column. And as you can see, when I calculate, my SO2 removal is 100%, give or take. Not 100% by the way, but it's close to 100%. And the simulation result is 100% SO2 removal compared with the experimental result is 96%. Well, I guess it is a good, it's pretty good comparison, but you know, things can never be the same because the simulation is the calculation of the simulation is equilibrium based for the real life absorption column, okay, kinetics, difference in temperature, pressure drop, hidden mass transfer, okay, limitation, all that kind of stuff do contribute to the slight decrease in the SO2 removal efficiency. And if you see here, I took this table as 6, which is taken from the references where I choose L/G ratio of 15. And the liquid flow rate, same with mine. Okay, if you see 4214, my flow rate is 4216. And then gas flow rate is, this is in standard meter cube per hours, and it is equivalent to this. And then carbon, calcium over sulfur molar ratio, if you see here, 0.028. This one is 0.0229. If you remember, if you remember when I did my simulation, efficiencies 96 and mine is 100. So I think it is a pretty comparable result, I would say, but just need to remember that experiment and simulation can be different. Okay, that would be all for me. Thank you all for listening. If you like the video, give it a thumbs up, and I'll see you guys in the next video.